I'm Roger Summons. I'm a Professor of Geobiology in the Earth, Atmospheric and Planetary Sciences Department at MIT. I'm also the PI of the MIT lead team of the NASA Astrobiology Institute. Our team studies the history of complex life on Earth, studies the geological and biological conditions that needed to come together to make the Earth habitable to complex multicellular organisms. We're also interested in the conditions that allow complex life to be maintained on Earth and potentially on other planets. My personal research interest is in the field of organic chemistry, and specifically in the area of natural products. Natural products are complex organic molecules that nature makes to allow certain functions in the cell or in the organism as a whole. And about 30 years ago I learned an interesting fact that complex organic molecules can be preserved in sedimentary rocks over very long periods of time. And here we have a ready-made tool that we can study aspects of biological evolution that you can't get at through the study of conventional fossils. It was actually organic geochemists who invented the term biomarkers. It's a term commonly used in the medical field these days, but organic geochemists termed the word as a shortening of biological marker compounds. And basically these are complex molecules that carry information about the organism that made them. Cholesterol is a very good example of a biological marker compound or biomarker. For example, everyone knows that cholesterol is a component of the steroids in our body. It's actually an essential component. We wouldn't be here unless nature had invented a way to make the molecule cholesterol. It's only when we have too much cholesterol that it becomes a problem. Cholesterol is a very stable molecule as well, so long after we're dead and buried you could probably find traces of cholesterol in the cemetery where our bodies were laying to rest. Another example of biological markers are pigments. Carotenoids and chlorophylls leave residues in sediments that we can detect in rocks as old as 1.5 billion years. So if you're looking at fossil pigments, then you have a way to study things like the history of plankton in the ocean. We also have markers for the earliest animals. We have markers that we can use to look at processes that take place during mass extinctions and in the aftermath of mass extinctions. And we also have organic molecules that provide a record of climate change, in fact a very long-term record of Earth's climate history.